Okay. All right, now we're recording. I'm still expecting one more. Morning. I recommend you take one, just for your own protection. Okay, we're getting close to 8:20. I am still expecting one more remote person, so if there's any evidence of another name popping up, if you would just let me know, I'd appreciate that. Okay, I'd like to start class with a few announcements just to kind of help everybody make sure they're keeping up with the things that they need to be doing, okay? And remind you of what's coming up. So after today's class, the next thing that you have to do is to finish up your first homework set. And I know that some of you have started working on it because I've been getting questions, which is expected, okay? Remember that homework is due 11:59 p.m. tonight, Eastern Daylight Time, okay? And Wiley Plus will not give you the points if it's after that time, okay? You can still see the problems. You can still even enter answers and it'll tell you if they're right or wrong. But if it's after 11:59 p.m., it won't give you any points, okay? Now remember there's a physics tutor, his name is Dave Shaibi, and I sent you, all of you, an email with a link to a Google Meet for his tutoring sessions. To remind you, they are Monday and Wednesday evenings from 6 to 8 p.m., okay? And so if it's during those times, I sent you two links. I sent you one for the Monday session and another one for the Wednesday session. So if it's tonight, make sure you go to the link for Monday, okay? And Google Meet is like Blackboard Collaborate. It's a virtual classroom. And you will be able to ask Dave questions, and he'll probably have a whiteboard app where he can write, and you can see what he's writing, okay? I'm available too. I have people send me questions, either to me directly or through Wiley Plus, which is fine. I'm happy to help. Let me give you a word of encouragement about these homework problems. They are the type that require systematic logical thinking, not intuitive gut thinking. There's fast and slow thinking. Gut thinking is fast, logical, systematic thinking is slow. We tend to prefer the fast thinking. It's easier. That's how we often get around life. Fast thinking. Physics requires systematic thinking. Slow, deliberate, analytical, logical. Okay? Thank you. That means when you read these homework problems, you very well might first have a first reaction of, I don't even know where to start. Okay, that's normal. However, you need to just think about it, read it very carefully. What is it telling me? And what is it asking for? If it asks for a volume, then the answer's got to be a volume, not an area. Or if it asks for an area, the answer's got to be an area, not a volume. Everything is very logical, okay? But it takes getting used to. So you'll probably have a lot of questions at first because we're training your brain to think systematically and logically, which is not the way most of us intuitively think. So it is quite normal to feel like the problems are a bit overwhelming at first, but you got to keep trying, okay? And maybe after you've had a little bit of help from me or the physics tutor, and you've had a few of those moments where you go, oh, that's what that means. File that away for future reference, whatever that might be. Okay? And bit by bit, you'll be developing skills like you develop skills for anything. Riding a bicycle, playing tennis, playing a piano. You're not born knowing how to do those things. They take practice. And this is the same thing. Okay? So you just got to keep trying and you got to ask questions until you have that click. And everybody has to click on their own rate. Okay? Just got to keep trying. And physics is all about practice. So there's going to be another problem set. So after the one tonight, the next one's going to be due Thursday night, 11:59 p.m. And that's going to be the pattern ongoing. I'll be posting that next set probably later today. And it will be our first problem set on concepts from chapter 2, motion along a line. Okay? Okay. And let's see. I'm going to be sending you later today the next video lecture. You didn't have one for today, but normally before every class, remember, you're going to have a video lecture to watch. That's your prep before coming to class. So I'll be sending you the one for Wednesday pretty soon. And it's quite likely going to have a few of those embedded little questions like that one lecture did. And you had to go to Blackboard and enter your answers like most of you did. So be aware that's probably going to happen again. In fact, that's going to be kind of ongoing. Okay, good so far. This is the week lab starts. Everybody should be in either a Monday or Tuesday section. There are no other sections. So you need to be in Monday or Tuesday. If you're Monday lab, we start today. Remember, we start at 1:20 in the afternoon over in the Science Center in room 136. Okay? I don't think I have any remote lab learners on Monday. So today's lab will be pretty straightforward for those of you that are in that section. I have remote learners on Tuesday lab. So there's going to be a kind of a more detailed procedure involved. And I'm going to be sending out an email with an explanation of how we're going to work with remote learners involved. Okay. So that will be pertinent to the Tuesday lab. So be watching for that. There'll be an email with some instructions. You do want to do a little bit of preparing before the lab to make you efficient at getting your lab done today. The lab manual, remember, you go to Blackboard and go to 110L, not 110C, 110L. It should be listed there in your classes. And when you go into that site, you'll find our lab manual. That's really the whole thing for lab, is that lab manual. And it's a hyperlinked PDF, so you open it up, and Adobe Reader or something will open it up, okay? And you start reading. Now, specifically for this week, read the syllabus Just a couple of pages. In fact, it's pages 5 and 6. Says syllabus. And then experiment 1, because that's what you're going to be doing this week. That's pages 17 through 21, but you'll just find it. It's experiment 1 in the lab manual. It might help you a little bit if you looked over in your textbook, Wiley Plus, chapter 2, section 3, about acceleration. That's involved in the lab. But we won't have that class till Wednesday. That happened this year because of COVID. The schedule got all messed up. Normally classes would start on Wednesday, not Thursday, and I'd have one more class day before lab, which is the day I need for acceleration. So I'm sorry about that. It's probably going to be one of the many ways that COVID is going to cause pain. Okay. All right. Any questions about anything I've said by way of what I call logistics? Okay. Hearing none. Let me pick up the example I was doing at the end of class on Friday. And then we'll go into more discussion about the topic for today. This was our first example in chapter 2. So I label it example 2.1. Let me remind you what it said, because I don't have the wording up anymore. It's a person playing softball, which is similar to baseball. Okay? The person hits the ball with the bat, standing at home plate initially, runs along the first base line, passes first base to the point I've labeled A, and then just backtracks to first base. That's the motion. Home plate to point A, and then back to first base. Okay? And I told you this distance D, 18.29 meters from home plate to first base, and the distance L from first base to that point I've labeled A is 6 meters. So I've drawn a sketch and I'm tabulating what I've been given. We're told the average velocity of the runner for what I called part 1 of the motion. That's going from home plate out to point A, just that part. We're told that's positive 4.67 meters per second. We're also given the average velocity for the total trip. I call that V average net. That means home plate out to point A and then the backtracking to first base. That average velocity is positive 2.29 meters per second. So this is all that's given. Then here's the question. What's the average velocity for what I call part 2 of the motion, which is just the part backtracking from A back to first base? Okay? I think that's where I left us on Friday. So that's where I want to pick up. Okay? Okay. So we've drawn a sketch, we've tabulated what we're given and what we need to know. The next step in the acronym, remember, is STEMS for solving physics problems. S for sketch, T for tabulate, E for explain the physics. So physics. Okay. What physics do we need? Well, we're given average velocities, a couple of distances, and we're asked for an average velocity. So I think the key physics idea is average velocity. That's pretty much it for this problem. Okay. We need to get an average velocity, and we're given 2 average velocities. All right. Let's think a minute about this one then. That's what we want. So who remembers? How do you calculate average velocity? Either what's its definition? What do you need to know?
Delta x over delta.
Okay, that's its definition. Delta x over delta t. Who remembers what delta x is called? Displacement. Okay, so I need the displacement for part 2 divided by the time interval for part 2, right? This is where you start to have that moment like, what am I supposed to do? Because do I know the time interval for part 2? Am I given any times whatsoever? No, it looks a little bit like it's a lost cause, doesn't it? But there must be a way. So let's take it a step at a time. So let's write down what we need to calculate for this problem. We need the displacement delta x for part 2 divided by the time interval for part 2. That's how I'm going to label it. But you got to be very careful in your labeling. All right. I think this denominator is the sticking point. I don't know the time interval for part 2, right? I claim we have enough information for the delta x2. I'll let you think about that for a minute or so. But the delta t2, what are we supposed to do? Well, we need to make use of everything we're given. I do have 2 different average velocities I'm given, yes? Apparently, I better learn something from these values. How about the first one? Let's look at that, part 1 of the motion. From home plate to point A, we are given the average velocity for that. From the definition, that would be the displacement for part 1 over the time interval for part 1, right? Okay, now I'm given the V average for part 1. Let's see what I can learn. Can I figure out the delta x1? Can you tell me anything about that? Displacement for part 1. Yes. So looks like you're telling me the value D. So let's see, part 1 is from where to where? Home plate to A. So what is it? So what did you do? You did D plus L, didn't you? Okay? That's what I'm going to write, by the way, D plus L. Do you see why? That's the displacement for part 1. And then delta T1. Now look at the formula, that, and that. What's the only thing I don't know in that little formula? What is it? Delta T1, right? So I ought to be able to learn what delta T1 is from this little formula, yes? We do lots of algebra here. So I need to be able to take this equation and solve it for delta T1. Just cross multiply. Looks like that. D plus L over V average 1. Okay? Lots of algebra. All right, so you told us what the D plus L is, right? If you don't want to do it in your head, well, it's up to you, but you're just adding the D and the L, and then you're dividing by the V average 1, positive 4.67 meters per second. Look at those units a little bit. You need to be able to convince yourself the meters cancel, and the final units are going to be seconds. I'll tell you what that number turns out to be. I'm going to give you an extra sig fig or so, because it's an intermediate step. I get 5.201 seconds. That's how long it takes the softball runner to run from home plate out to point A. Okay? So I've learned something, delta T1. Can I put that right here and get my answer for the problem? No. Does that say delta T1? Can't put delta T1 there. That's the time interval for the backtracking part only. But I bet I'm going to need that delta T1 somehow. But that's all I can learn from V average 1. So now let's do the V average net and see what we can learn from that. Okay? So now we're going to do the net motion. V average net is delta X net over delta T net. Got to be really careful about labeling things because there are a lot of parts to the problem and you can get confused. Okay, I know the V average net. Let's see, can you tell me what the delta X net is? Thought here. Okay, displacement versus distance traveled. Yeah, okay. It's delta X, that's displacement. D plus 2L would be the distance traveled. But the displacement there ends up there, D. Okay? All right, so D over delta T net. The only thing I don't know is delta T net. So use your algebra and solve for delta T net. That's D over V average net. So 18.29 meters over 2.29 meters per second. Again, the meters will cancel in the units. You'll have seconds left over. I get 7.987 seconds. Always good to do little sanity checks along the way. Does it make sense? Well, there's the time for the total trip. Home plate, point A, and backtrack to first base. It had better be larger, should it not, for the time for just the first part? It has to take more for the whole trip than just the first part of the trip. And it's a little bit it's larger by a little more than 2 seconds. It seems reasonable. Okay. Now I contend I have enough information to get back to the thing that they want. The V average for just part 2. Remember, part 2 is the backtracking from point A back to first base, just that part. Okay. That's like I wrote over there, delta X for part 2 over delta T for part 2. Who can tell me what the delta X is for part 2? Warning, it's tricky. Excellent. Negative L. That's important to see that. You see why? For this part, backtracking from A to first base, notice you end up to the left of where you started, i.e. you end up on the negative X side of where you started. The displacement is negative. It must be included or the answer is wrong. Okay? What's the magnitude of it? Well, just what's the difference in the X values between those 2 points? It's L. Okay? So it's really vital that you understand what I put there in that numerator. Negative L. And if you didn't put the negative, Wiley Plus is going to say your answer is wrong. Now, how about the delta T2? Any thoughts on how to get that? Yeah. Sure. The delta T for the whole trip minus the delta T for just the first part. That will leave me the delta T for the second part. All right, so that's negative 6 meters over 7.987 seconds minus 5.201 seconds. Don't round off intermediate values, by the way, or you'll accentuate your rounding error, and then Wiley Plus still might say you're wrong, because you get a 2% tolerance with Wiley Plus. So what does that give you when you put it in your calculator? Negative 2.15 meter per second. And always mark your final answer very clearly. Hey, folks, there's my answer. Okay? Everybody understand how we did that example? Very typical Wiley Plus type problem. And it's a real world application, right? This is stuff that happens. Okay, so that's indicative of the kinds of problems you'll find in Wiley Plus. Now what I want to do, I'm going to have to pull this screen down. So hopefully you're at least over here in terms of your note taking. I'm going to go to my projector, hopefully. Looks like it's going to power it off on me. Doesn't like being muted very long. And I'm going to start talking about, the concept for today is instantaneous velocity. How are we doing on the writing of this? Has everybody got it? I need some board space. Instantaneous velocity. That was part of my video lecture for Friday. Okay. Okay, there you see the learning objectives for today's discussion. First one, given a particle's position as a function of time, calculate the instantaneous velocity for any particular time. Notice we already had average velocity as a concept. That's the displacement divided by the time interval, and it's over a finite amount of time. Average velocity is always over a finite time interval. Instantaneous velocity is at an instant, hence the name. Okay? How do you calculate such a thing? That's what the topic is. Okay? Let me give you the definition of instantaneous velocity. It was in the video lecture. Note the symbol. Just a simple old italic lowercase v. All right? It's defined to be, okay, here comes calculus. This is what's called a limit in calculus. It's the limit as the quantity delta t approaches zero. Becomes what's called infinitesimal, which is basically approaching zero without actually technically landing on zero. Okay. And what is it we're taking the limit of? You gotta take the limit of some quantity. That, delta x over delta t. Delta x over delta t was just the definition of average velocity. So instantaneous velocity is just a special limit of average velocity. Take average velocity for a time interval delta t and pass to the limit where delta t becomes vanishingly small. And you're finding then the velocity at an instant. Okay? And all I did here was write out delta x over delta t. Specifically in the numerator, I wrote out delta x. Delta always means change. So delta x means change in x. X final minus x initial. X final minus x initial. This notation means x at time t, that's x initial, and x at time t plus delta t, that's x final. So that's just x final minus x initial over delta t. Now to get used to calculus, one of the things you have to get used to is this kind of a limit. And your algebra skills should be telling you that this looks bad from an algebra perspective, because you're telling me to take a fraction, right, numerator and denominator, and pass to the limit where that denominator gets vanishingly small. And didn't my algebra teacher always taught me that if you have a zero in a denominator or something that's approaching a zero, you're in trouble. Okay? That's not a defined quantity. So your first reaction ought to be, well, you people don't know any algebra. What are you doing? You're crazy. Okay? This is where the brilliance of it came in, because the numerator is also becoming vanishingly small in just the right way, so that the ratio of the numerator to the denominator has a finite answer for that limit. It's really amazing. Okay? The machinery of this process of taking this limit is given a name in calculus. It's called taking a derivative. That's what that limit means. And what are we doing? Got to get used to the notation. This is the way we denote all that limit stuff, because it's too much to write. So we want shorthand. This is just another way to write all that, but you got to be used to it. dx by dt. Here's how I think of it. Derivative of x with respect to t. That's what that's telling me in code. I must take the derivative of the function x with respect to the variable t. Okay? So we say that instantaneous velocity is the derivative of the position with respect to time. If you've had calculus, you've probably heard of the phrase rate of change. A derivative measures the rate at which a function is changing. If you think about velocity, that's exactly what it's telling you. It's the rate at which the particle's position is changing. So we need to be able to do this kind of derivative. I'm going to show you the ones you need to know. And I know some of you are just in calculus for the first time, and there's no way your calculus professor has taught you yet how to do it. They will. So I'm just going to tell you the things you need to know, kind of shorthand, shortcut. Okay. All right, here's another thing to remember. Whenever you do a derivative, like here, of x with respect to t, this is one of the things that was in my video lecture. If you go to a graph of that, x versus t, the derivative is the slope of the tangent line. Okay, I talked about that in the video lecture as well. So if you have a plot of x versus t, the velocity is the slope of the tangent line to the graph at any given time. All right, so what I'm going to focus on now is just practice with what's called differentiation, taking a derivative. And I'm going to tell you the common derivatives that you should just know as far as this class is concerned, okay? All right. Here's the first one, probably the most important. A so-called polynomial function. We're thinking x is a function of t, so a polynomial function of time. This form, x equals c t to the n, where the c and the n are just constants. Okay? So any equation like that, I mean, an example would be something like that. X equals 3t squared. Constant, t raised to the power of a constant. That's a polynomial. What is the result when you take the derivative of a function that has that structure? Here it is. This is going to give you v, right? Because dx by dt is v, instantaneous velocity. I'm just telling you the rule. I'm not proving it. So you just have to accept it for now. You want the proof? Your Math 110 professor will provide that. But the rule is easy. To take the derivative of that function with respect to time to get v, you bring down the exponent and multiply it out front, n. Keep the constant c out front. And then the t, look what happens to the exponent. It gets reduced by 1. All right? That's the rule. We'll practice with that in a minute. Here's another one. What if the x is a sinusoidal function of time? In other words, as a constant sine of a constant times t. Sine function. Remember the sine function? That kind of expression is going to be important when we study what's called oscillations. Something connected to a spring that's oscillating back and forth, repeats its motion, like a sine curve repeats. Okay? What's the derivative of a sine? Because if that's x, then here's how you get v. I'm telling you what that derivative is. You bring out the b out front, you keep the c, and the sine becomes a cosine. And then bt. So you'll hear your calculus professor say kind of shortcut language like, oh, the derivative of sine is cosine. But watch out, a factor of that b comes out front, which I'll explain more about in a minute. Well, if you have sines, you could also have cosines. What if your function x is c, that's just a constant, cosine of a constant times t? What's the derivative of that function? I'm just telling you, because that derivative will give you v. You get a negative sign, bring the b out front, c sine of bt. So you'll hear your calculus professor say the derivative of cosine is negative sine. And then lastly, an exponential function. X equals a constant e to a constant times t. That's the exponential base. That's an easy derivative. The derivative of the exponential is the exponential. You have to bring down a factor of b is the only subtle part. So the result for v is bce to the bt. Okay? All right. Ready to do a little practicing with these? Okay. Suppose a particle's position is given as a function of time. There it is. I'm just telling you. X equals 2 plus 3t minus 4t squared. Question. What is the particle's velocity as a function of time? Let you sit and think about that a minute. Okay. So now I'm telling you what x is. 2 plus 3t minus 4t squared. I'm giving you the position as a function of time. What's the velocity as a function of time? I'll give you a hint. You need that polynomial rule. If x equals ct to the n, then v which is dx dt, is n times c times t to the n minus 1. Okay. Now, for those who haven't done calculus, this is probably your first attempt at doing any of this, so you're probably a little uncertain. For those of you that have done calculus, you're probably saying, I know this. Okay. Who knows what the answer is, feels comfortable sharing it? Yes. So v, doing the derivative, you're telling me is 3 minus 8t. Yes? Okay, let's make sure we see how that comes out. Here's one good thing about a derivative. You got some terms added together, just take the derivative one by one, term by term, okay? So the first term is 2, just old 2. Now, note something. You can think of it like that, right? Isn't anything to the 0 power 1? So you can think of that as 2 times t to the 0, and then use that rule. You see what happens? What do you get when you take the derivative of just that part? What's this thing that sits right here? In this case, 0. You're multiplying by a 0. Yep, it's over. It's already done then, isn't it? 0. The derivative of any constant is 0. Because derivative is rate of change. A constant isn't changing. Okay? All right, so there's nothing there. So now go on to this term next. 3 times t, and apply that recipe. Well, of course, that's 3 times t to the 1 power, right? So you bring down a 1, and you got a 3, and now the t becomes t to the 1 minus 1, or 0. But anything to the 0 power is 1. So all that's left is just the 3. And then you got the minus 4t squared. And again, apply that rule. You got to keep the minus. That just gets carried along. And the 2 comes down, and 4 times 2 is 8. And the power of t goes down by 1, so it goes from the second power to the first power. Okay? And now you've got the function that tells you the velocity. All you got to do is tell me the t, and I'll plug in and tell you the v. Okay? Note something to get used to with problems like this. Typical in your book. They give you those numbers like the 2 and the 3 and the negative 4 in that formula for x. And then they say things like, well, they don't say it here, but they would probably say things like, where x is in meters and t in seconds. You have to figure out for yourself what the units are on those, the 2 and the 3 and the negative 4, because they do have units. Okay? But they're just not telling you what they are. Just remember, the x has got to be in meters and the t has got to be in seconds. So every term has got to ultimately be in meters. All right, now let me show you something else that you need to know. We'll use this once in a while. This is what you're going to use by far the most for a while now, okay? But I just want you to be aware of a couple more things. The so-called product rule when you take a derivative. Suppose you've got the particle's position is expressed as 2 separate functions of time multiplied together. So the position as a function of time is one function of time I'll call f times a different function of time I'll call g. How do you take the derivative of like something like that? Because that's what you got to do to get the velocity, is take the derivative. Well, when your function is actually a product of 2 functions, you use the product rule, which says really quite simply this. If the 2 functions are f and g, take the derivative of the first function and just multiply by the second, plus take the first function and multiply it by the derivative of the second. Got to break it down into parts, it turns out. The derivative of the first times the second, plus the first times the derivative of the second. Your calculus professors will probably prove that for you. Okay? So let's do a little bit of practice. Let's say we're given a particle's position as a function of time is this formula. That looks interesting. X equals 2t squared times sine of t. That's how that would be written. If you want to put the t in parentheses, you're welcome to. That means sine of t. But a lot of times books won't do that. Okay? And I want the velocity, v, for such motion. So that means I have to calculate dx by dt. But that's really, you can see it very clearly. That's a function of t, and that's a function of t. Right? If you want to apply that formula, you can think of that one as the f function and that one as the g function. All right, let's see what we get when we apply this new rule, the product rule. So you guys help me out, okay? First piece of the product rule. Take the derivative of the first function with respect to t, and then just multiply by the second function. All right, so what is the derivative of the first function here? What do you get? Say again? 4t, right? 2t squared, apply the polynomial rule, bring down the 2, 2 times 2 is 4, reduce the exponent by 1, so 4t, that's the derivative of the f. And that just gets multiplied by the g, so times sine t, yes? Then plus, follow the product rule, next take the f function, 2t squared, and multiply that by the derivative of the g function. There's the g. What's the derivative of sine t? Cosine t? So times cosine t. That's it. Not much more you can do with that. But that's the velocity as a function of time, if that's the x. Okay? Then you tell me the t value, and I'd plug in, and I'd tell you the v. All right, one more idea that we just did that. What's called the chain rule. That is often what gives people headaches. I'm going to show you my way of thinking of the chain rule, but I'll state it first more formally, and then I'll show you the way I think of it. The chain rule is when you have the particle's position expressed as a function of a function, f of g of t. Those take a little getting used to, okay? But if that's what you've got, then the velocity is calculated using the chain rule. V is dx by dt is df by dg times dg by dt. Okay? Okay, that's what's called the chain rule. So we're going to practice, and I'm going to show you how I use it. Suppose a particle's position is given as a function of time x equals sine of, now look at that argument, a little more complicated than something I've shown you before. The argument of the sine is 2t squared. Not t to the 1 power, but t squared inside there. So that's a sine of something a little bit more complicated, yes? That's when you need to use the chain rule. Sure, absolutely. Okay. So how do you do it? Here's how I think about it. I'm going to call this sine, and this argument here, I'm going to call just a blob. Okay? That's sine of blob. How do I take the derivative of sine of blob? The derivative of sine blob is cosine blob, because the derivative of sine is cosine, multiplied by the derivative of the blob itself. Okay? You got sine blob? Then the derivative is cosine blob multiplied by the derivative of the blob. That is what that says. It just doesn't say it with those words. So let's try that, okay? If x equals, oh, I need to use black, don't I, to be consistent. If x equals sine of 2t squared, that's the blob. the 2t squared. So to get the velocity, dx dt, it is, according to the chain rule, derivative of sine blob, cosine blob, blob is 2t squared, right? Multiplied by, dot for multiply, the derivative of the blob. Now just look at that. The blob's not that complicated. 2t squared, right? That's a polynomial, isn't it? So what's the derivative of 2t squared? 4t. So this cosine of blob gets multiplied by a factor of 4t. Okay? I had a sine blob, the derivative, cosine blob, multiplied by the derivative of the blob. Okay? You can apply that even to the more trivial case. What if I just gave you this? Sine of t. Now think of t as the blob and apply the chain rule. I have sine blob, then the chain rule tells me the derivative is cosine blob. Oh, wait a minute. That would be then cosine of the blob now is t times the derivative of the blob. There's the blob, t. T to the 1 power. What's the derivative of that? It's 1, isn't it? 1t to the 1. 1 times t to the 0, which is 1. 1 times 1 times 1 is 1. Well, nobody writes that 1 like that, right? They would just write this as cosine t. That's how the people would write it. And that's what I told you on the first slide. Derivative of sine is cosine. The chain rule works even for simple situations, but you wouldn't use it for a simple one. Now, for now, focus on that one, that derivative. Polynomial function of time. That's what you're going to need the most. Bit by bit, as the semester progresses and we learn more physics and get to more complicated situations, we'll start using product rule and chain rule. Okay? All right. Now, here's what I want to do next. Let me get set up with another example problem. We'll talk about it a bit, and then we'll finish it at the beginning of class on Wednesday. So it's there on the screen. When I say I'm doing an example, I will tell you, this is the second example in chapter 2 that I'm doing here in class. So example 2.2, and what it is that it's going to be focusing on, instantaneous velocity. And whenever I'm doing an example labeled example, not just practice or something, but example, then I'm doing for you, in essence, a Wiley plus problem. Indicative of the homework kind of problem, okay? So it's well worth your time to take good notes, because that means it's going to help you do homework. Let's at least get the sketch part of this going, right? That's the first step, yes? Here's the scenario. We have a radio-controlled truck. You seen these things? I mean, you think of a drone, right? That's radio-controlled, right? But this is a radio-controlled toy truck called an RC truck, and a radio-controlled toy airplane. And they're both moving along a driveway along the same x-axis. Some kids are playing with them, for example. The position of the truck is going to be labeled xt, and the position of the airplane is going to be labeled xp, and I am given their functions of time. X for the truck is 2t minus 0.4t squared. And x for the plane is 4 minus t plus 0.25t squared, where both x coordinates are in meters and t is in seconds. That means you need to figure out the units on the 2 and the negative 0.4 and the 4 and the negative 1 and the 0.25, because they have units, but they're not telling you what they are. Okay, so we're told the x-coordinate of these two particles, just think of them as particles, on the same x-axis as a function of time. And they're going to ask us things about the motion of these two things. First thing they ask, at what instant do the truck and the airplane have the same velocity? Okay, let's start setting this problem up. First thing is a sketch, right? This problem gives us no picture whatsoever. We have to create our own. One of the tricks, one of the things you learn in physics to solve problems efficiently is how to draw a sketch that's useful to you in solving the problem and ignores extraneous details that would only confuse you. Okay? I know that these particles, and that's how I'm going to think about them, are moving along an x-axis. So I'm going to draw an x-axis. I'm even going to put some tick marks on it. 0, 1, 2, 3, 4. For reasons you'll learn, that's enough. Now I'm going to draw my sketch, let me be very clear, at one particular time. Time 0, the beginning. Okay? Because they are moving, yes? So I can't draw a sketch to get all the times because they're moving, they're changing their x. Let's at least get the initial picture. All right. Let's tabulate what we are given. We're given the x of the truck. We'll just write it, 2t minus 0.4t squared, and the x of the plane, 4 minus t plus 0.25 t squared. I contend that from these two formulas, I can tell you where the objects are, can't I, at any time? Just plug in the t to get the x. For my sketch, I want where they are at time 0. So, okay, tell me, where is the truck located at time 0? Letting people think about it. Ah, yes. It's at 0. Plug in t equals 0 to this formula, and the x comes out to be 0. So the truck, I'll just represent it as a dot and label it t, is right there. Don't draw anything more complicated than that. Everything in this chapter is a particle. Okay? Where's the plane at time 0? It's at 4. Plug in t equals 0, that's 0, that's 0, and there's a 4 left. So the plane is at x equals 4. P, label it. Okay? All right, here, that's where I'm going to pause for now. So let's just give you a little preview of what's coming up. Okay? Part A asks us, at what instant do the truck and the plane have the same, notice what it's asking, when do they have the same velocity? Well, I've got to find the formula for the v for each thing, don't I? And then find out when the v's are equal. How do I find the formula for the v for each thing? I take the derivative, because that's the x for each thing as a function of time. So I'll have to take derivatives of that and that. Should be able to do that, and then I'd have the velocity formula for each thing, right? Then it's not hard from that point to find out when those v's are equal. And that'll be the first part. So that's where we'll pick up on Wednesday, okay? Okay, very good. Thank you.